This is the second half of the lesson for the fundamental theorem of algebra. To write the polynomial function given the zeros, we need to write the zeros in x minus k form so that we're actually writing the factors. And now we'll need to FOIL them all out. I'm going to multiply these two first. So I FOILed the first two terms, and now I need to distribute the binomial x minus 2 to the trinomial x squared minus 8x plus 15. So distributing the x first, and now distributing our negative 2. I'm going to use the method that we've been using in class recently where I line everything up under its like term. And we get a minus 30 at the end. We combine, and we get x cubed minus 10x squared plus 31x minus 30, and that is what our f of x is equal to. Just as we did in part A, we're going to write our x minus k's and set up our factors. We have to be careful this time because k happens to be 1 plus I, so I need minus 1 plus I in parentheses. But our complex conjugate theorem told us that if we have 1 plus I as a root, we'll also need 1 minus I. That way, when we FOIL and multiply all this out, we don't get i's in our final polynomial. So now that we simplified that, we can go ahead and start multiplying. I'll multiply the two trinomials first. I highlighted as I went through and multiplied which color I got from distributing which part of the first trinomial into the second trinomial. From here, we're going to simplify. And then the next step that we'll take is multiplying that x minus 5 times our simplified polynomial. Don't forget, I squared is really equal to negative 1, so I'll plug negative 1 and continue to simplify. And now we can distribute our x and our negative 5 through to the trinomial. So hopefully we came up with the same answer here. And I want you to go on now and try part C. Don't forget what your complex and your radical conjugate rules are. If you have negative 2 minus the square root of 5, then you must have negative 2 plus the square root of 5. Common mistake here is that somebody's going to give me a positive 2 plus the square root of 5. Please be careful with that. So double check all of the work, and especially because it's late, so there could be a mistake. So if you find one, post it on Edmodo immediately. Descartes' rule of signs is where we've got a polynomial function, f of x, and it has real coefficients, just like what we've been dealing with all along. We can actually start determining the possible types and number of each type of zeros that we're going to have based off of this rule. The number of positive real zeros is equal to the number of changes in signs of the coefficients, or it's going to be less than that by an even number. So in f of x, let's say that we have negative 4x to the 5th power minus 3x to the 4th plus 2x to the 3rd power minus 7x plus 3. If we count the sign changes here, what we're dealing with is we're starting with a negative, stays negative, up goes positive. There's one sign change. Up goes to a negative. There's another sign change and goes to positive. So there are 3 sign changes in this particular polynomial function. That means there will be at most 3 positive real zeros, or there could be 1 positive real zero, because 3 minus an even number of 2 gives us 1. There won't be any positive real zeros that we're dealing with. That will be 2 of them, or we won't have 4 positive real zeros in this case. the number of negative real zeros is equal to the number of sign changes of the coefficients of f of negative x. So instead of where we see f of x, we're going to plug in a negative x in its place. And then we have to simplify and clean things up a little bit. So negative 4 times negative x raised to the 5th power minus 3 times negative x raised to the 4th power plus 2 times negative x to the 3rd minus 7 times negative x plus 3. So if we simplify this a little bit here, f of negative x is going to give us here, we've got a negative power, a negative raised to an odd power. So that's going to stay negative, but there's a negative out in front. It's going to become plus 4x to the 5th. Here, this negative x raised to the 4th power will become positive. There's a negative out in front, so it stays as negative 3x to the 4th power. The x cubed term, negative raised to an odd power, gives us a negative, times the negative that's out in front, we have negative 2x cubed. Negative x times a negative 7 gives us plus 7x plus 3. So now if we go through and we count our sign changes, we start off positive and we bump to negative. There's one sign change. It stays negative, changes to positive, there's 2 sign changes, and it stays positive from there. So there will be 2 or 0 negative zeros that are real numbers. Let's use Descartes' rule of signs to talk about the possible different types of zeros we will have for this particular function and how many of each type of zero we might get. So if we look at f of x, I started at a positive, it moved to negative, stayed negative, changed to positive. There are 2 sign changes here. So that means that there could possibly be 2 or, subtract by an even number, 0 positive real zeros. If we take a look at f of negative x, meaning we're going to plug in negative x wherever we see an x and then simplify things. So when we go to simplify, a negative raised to an even power makes it positive. There's a positive 2 out in front. It's going to be a positive 2x to the 6th. A negative raised to an even power makes it positive, times the negative 3 out in front makes it negative 3x squared. Negative 1 times a negative x gives me a plus x, and then we have plus 1. So if we look at our sign changes here, I start positive and move negative, change to a positive again, and then it stays positive. So there are 2 sign changes here. Since there are 2 sign changes, that means we're going to get 2 or 0 negative. Real zeros. So now we can use this information to fill in a chart and see what all of our possible different cases might be. We're going to use the following chart to help us determine how many of what type of zeros we end up with when solving this polynomial function. When looking at 2x to the 6th minus 3x squared minus x plus 1, we determined that there were 2 sign changes in f of x. So that means we're going to have 2 positive zeros
or we're going to have 0 positive zeros. But we also determined that there could be 2 negative zeros, or we could have 0 negative zeros. So there could be cases where there's 2 positives and 2 negative answers. There's 2 positives but no negative answers. 0 positive, 2 negative, or no positive and no negative real number answers. So what that means then is we have to use the idea of the fundamental theorem of algebra. That tells us that the degree is the number of zeros we expect to get. So we need to get 6 zeros no matter what's going on with how many positives and negatives. This is going to help us figure out how many imaginary solutions we could end up with. So if we've got 2 positive, 2 negatives, we need 2 imaginaries to make up the 6 zeros. If there's 2 positives, 0 negatives, we're going to need 4 more imaginary solutions. If 2 of our answers are negative and we don't have any positives, then we're going to need 4 imaginary solutions. And if there's no positive reals and no negative reals, all 6 of our zeros are going to be imaginary numbers. So we could state for our zeros that positives we're going to have 0 or 2. For our negative zeros, again, we could have 0 or 2. And for imaginary zeros, we're going to have 2, 4, or 6 imaginary zeros in the solution to this problem.